The obvious reason why we do this is because the acquisition time to LEO satellites is much, much longer from a geo relay than you could have from, for instance, downloading the data over Nordic radio frequency ground stations. So the instantaneousness of the data is much, much higher if you use data relay systems. I mentioned the optical ground station, and on the right-hand side, you will see how many satellites with optical terminals have been already tested and commissioned, actually. Maybe one special would be the LADI mission, which was a NASA mission to the moon, where the optical ground station participated in communication with a satellite that was circling the moon. The ground station is not only used for that, it's also used for classical astronomy, for asteroid and NEO detection, for quantum communication experiment, and feeder links, and I will come to that. Now a bit of history on quantum comms, where ESA, for the first time, we established in 2001 a link with Professor Zeilinger from the Institute of Quantum Optics and Quantum Information to embark on a cooperation in quantum communication technologies. And within the next years, 2004, quite a number of inter-island experiments were performed. We even held the world record in long distance of quantum key distribution over 150 kilometers until in 2016, the Chinese quantum communication satellite MISUS was launched. And they, of course, trashed all these ground-based records with a satellite from space. And ESA was, and I would like to thank the Chinese Space Agency for that, was invited to participate from its ground station. And I will show a short time-lapse video on that. And okay, but from 2018 or 17 onwards, all of a sudden ESA woke up on this technology. And now we have two activities, Quartz and QKDSat, ongoing in development in order to be launched in the coming 2-3 years. And we have a strong cooperation with the European Commission on the SAGA program, which was launched to establish a cyber-secure communication infrastructure in Europe, space and ground-based. And now you will see a nice time-lapse video. Its integration time is about 20 seconds. That's why you see a line and not a dot. And you see how the satellite is moving across the sky. And I show you this because it is a very nice thing, because the satellite uses a green beacon and the ground station a red beacon. And so you can actually see the tracking of a satellite, of a LEO satellite in orbit. And of course, you don't see the quantum link, because that is, of course, with single photons and invisible. So that is something that is not visible on this one. Now, optical and quantum communications, the challenge. So what is the challenge that we're facing? Yeah, the problem is radio frequency communication is as old as two satellites, as old as satellites. So from Sputnik, okay, maybe that was not a real communication link, but still, it started there, while optical communication was only first time tested in the 90s. So optical comms technology, unfortunately, is still considered an unproven technology, and satellite operators are really reluctant to implement on it. And the cloud coverage of optical ground stations in direct-to-earth links, of course, is a risk factor that can be mitigated by multiple ground stations, but they're not available yet. So there is a bit of an issue here. So what is the consequence? It took ESA 26 years from the first developments to launch SILEX. And the first in optical comms, and the first quantum communication technology took 15 years, but what was not even launched by ESA at the end, but by the Chinese Space Agency. So having identified this dilemma, ESA embarked on the Optical Communications ScyLight activity, which is a dedicated dedicated telecommunications funding scheme for European and Canadian industry, indeed, to support specifically optical comms, photonics, and quantum technologies, and to provide demonstration missions. The Optical Communication ScyLight budget is at the moment in the order of 170 million euros, and we have 21 participating states. And what is the roadmap? What are the technologies that we would like to develop? So maybe they can be a little bit categorized. It's difficult to do that, but in the following 6 groups. So space and airborne optical communication terminals, reliable transmission through the atmosphere, feeder links and optical ground stations. And Jean-Paul talked about gigabits and tens of gigabits. With feeder links, we like to tap to feed optical future telecommunication satellites in the range of terabits, because these satellites already exist, fed by radio frequency systems. But of course, feeder links, optical feeder links, could support and relieve the strenuous licensing requirements in radio frequency. So we're working on that. We're working on quantum key distribution, onboard photonics, photonic integrated circuits, a topic that we will hear about this afternoon. And we would like to provide demonstration missions. This is a bit loaded view graph, I know, but it goes a little bit into more details in what we're looking at, like modulation, coding system, ranging, time, frequency transfer via optics. Standardization is a very important topic because we would like all the ground stations that are being developed to be able to operate with all the satellites so that everybody can take advantage of those. Terrestrial networking and routing concepts, and very important, laser safety, of course, if you shoot through the sky. Maybe in terms of cybersecure quantum key distribution technologies, we're looking into quantum sources, and if a quantum memory could be developed within the coming years, it would give a great deal of help, a great deal in the to reduce the complexity of the systems that we need to deploy. And we'd like to provide demonstration missions, which brings me kind of a little bit almost to the end to introduce Hydron, the high throughput optical network. And this is a demonstration mission that we're planning to demonstrate all these technologies that I mentioned before. The vision of Hydron is to develop the world first optical transport network at terabit capacity in space. And it's this extension of the terrestrial fiber network seamlessly into, and that's the buzzword, the fiber in the sky, as we call it. And maybe this is a little bit of a depiction of how Hydron should eventually look like. So you see a number of geostationary satellites connected by WDM inter-satellite links, connecting also low Earth orbiting satellites and airplanes, and being seamlessly integrated into the terrestrial fiber network. You see some ground stations there. And you also see a potential extension of Hydron, of the link into deep space, into links to the moon, where we're also already looking into the Lunar Orbital Platform Gateway from NASA, an ISS, if you will, that will circle the moon. And we would like to implement that node also into Hydron. Of course, ESA cannot finance all that. That would be impossible. But what we will do, we will devise 2 demonstration missions on a piggyback on existing or to be launched telecommunication satellites, one on a GEO and one on a LEO, in order to demonstrate the individual technologies that are necessary, and then leave it, of course, up to industry to pick up and make something and make it big. And having said that, I would like to thank you for your attention. And if you would like to learn more about ScyLight, about the funding possibilities, how to make business with ESA, please do not hesitate to contact me at zoran.sodnik@esa.int. Thank you very much.